everybody. Sorry I can't be with you today. So hopefully you've had a chance here to read through the opener and talk in your table groups about what is wrong with the simulation designs. I hope that for this first one, this is the part that you wanted to say was wrong. In this case, repeats are okay, since we're dealing with percentages of adults rather than individuals. The problem here is that if, for example, if the first person chosen was 18 and they are considered an obese person, right, based on our labeling scheme here, then the probability of the next person being obese is actually going to be 25 out of 99, which is about 25% rather than the 26% that we are wanting to work with. So in this case, because of the percentages, it's okay that we have repeats. That's what we would like to have. So then for part B, the problem with part B is that the numbers haven't been assigned properly. So the labels, numbers 0 through 9, are not being assigned. I guess you could look at this another way and say that, like, if we do rand int 0, 9, and then whatever number shows up tells us the number of babies that are male, but that's a different probability. If we just select like one number here from 0 to 9, that's a 1 in 10 probability, not a 50% probability. So that's another way that you could describe it as not being appropriate. But I think the main problem here is that our numbers aren't assigned. So we're going to get into our probability rules today. If you don't already have your packet of formulas and tables, now would be a good time to do so. We are now going to be in the middle column in our formula sheet, all these formulas about probability. Now we're not going to do all of these in this chapter, chapter 5, but we're going to get through the first couple of them here. But we need to talk about some just basic probability rules. And a lot of the stuff we're going to talk about initially, I assume you already have some kind of experience with. So let's just make sure we have all of our definitions appropriate. So what is a sample space? A sample space is the set of all possible outcomes of a chance behavior. Possible outcomes of a chance behavior. So, for example, if we're going to flip a coin, assuming that it's a fair coin, then I will have two possibilities in my sample space, heads or tails. If I roll a die, a regular six-sided die, then my sample space will include all of the 6 possibilities for that six-sided die. You could have the sample space of a compound event, like the sum of 2 dice that have been added together. The smallest sum of 2 dice is going to be 2, and then this is going to go all the way up 9, 10, 11 to 12. So the sample space is the set of all possible outcomes of that chance behavior. So we're going to get into probability models, and one of the things that you need to know how to deal with is what's called the fundamental counting principle. So the fundamental counting principle tells us that, for example, if I was going to flip a coin 3 times, and I'm interested in the total number of possible outcomes in the sample space, then I can use the fundamental counting principle to help me figure out the total number in my sample space. So for example, like if I flip a coin 3 times, okay, I could have heads, 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 I could have heads, heads, tails, heads, tails, heads, tails, heads, heads, tails, 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 and so on. Tails, tails, heads, tails, heads, tails, heads, tails, tails. Okay, well, so I can count them and see that there are 8. But so what the fundamental counting principle allows us to do is to actually figure out the total number of outcomes without having to list out all the possibilities. So I've got 3 coins, and each of the coin flips are independent of each other. So on the first flip, I have two possible outcomes, either heads or tails. On the second coin flip, I have two possible outcomes. On the third, I have two possible outcomes. And so if I multiply them together, then I have 8 possible outcomes. So does order matter? The answer is yes, because if I want to count all of the things that are in the sample space, then I do want to consider that, say for example, heads, heads, tails is different from heads, tails, heads. Now their probabilities aren't going to be different, but their order is going to be different. So what is a probability model? So probability model is basically like a way to organize probabilities together into a table. So I can say, let's let X be the number of heads in 3 flips of a coin. So I'm going to make this little chart here. It's like a sideways T chart. And so I'm going to put X here, and then I'm going to put P of X, the probability of that event. So the smallest number of heads that are possible in 3 flips of a coin is 0. I could have tails, tails, tails. Now, P of X is the probability of that happening. So here I have my whole sample space. How many of those 8 have exactly 0 heads? I would say 1 out of 8. And then you would continue filling out the table in the same fashion. So then I could also have 1 head, exactly 1 head in 3 flips of a coin. And so I want to count them. I've got tails, tails, heads, or tails, heads, tails, or heads, tails, tails. There are 3 out of 8. 2 heads out of 3 flips of a coin, you can count them up. There are 3 out of 8. And 3 out of 3, there is 1 out of 8. Okay, so in the top part of our table here, this shows all the possible outcomes or events that can happen and the probabilities for each one of those events. Now notice that if I add all of these together, I get 8 out of 8 or 1. So in a probability model, just like in a density curve, all those probabilities have to add up to be 1. So what is an event? Well, all of these things that we were talking about are events. An event is a subset of our sample space. So when I said let X equal to 1 head out of 3 flips of a coin, that means I'm going inside the sample space and selecting something that's going on inside that sample space. That's called an event. All right, let's flip the page. So imagine flipping a fair coin 3 times. Describe the probability model for this chance process and use it to find the probability of getting at least 1 head in 3 flips. Okay, well we just did the probability model. Okay, that was on the same, the thing we just made on the other page. Like this, P of X, blah, 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 1/8, 3/8, 3/8, and 1/8. All right, so now it's asking us to find the probability of getting at least 1 head in 3 flips of a coin. So X is, remember, the number of heads in 3 flips of a coin. I want that to be at least 1. Okay, so then I can look at my thing here, my probability model, and getting at least 1 means that I could have 1 flip of a coin, or I could have 2, or I could have 3. And I'm throwing some formulas at you, which we haven't yet learned about, but what you can do here is we can just add them together. So the probability of getting exactly 1 is going to be 3/8, exactly 2 is 3/8, and exactly 3 is 1/8. And so the probability of having at least 1 head in 3 flips of a coin is 7/8. You could also do this as a complement. The probability of X greater than or equal to 1 is 1 minus the probability that X is less than 1. Okay, well another way to write that would be 1 minus the probability of X equal to 0. And so that would be 1 minus 1/8, which is going to be 7/8. So I'm, again, throwing out a couple of these ideas that we haven't really talked about. So let's talk about the rules for probability. So rule number 1 says for any event A, the probability of A lives between a specific range of values. So the smallest probability is 0, meaning it never happens, and the largest probability 1, meaning that it always happens. Rule number 2 says if S is my sample space, then the probability of S is equal to 1. So if I add up all the things in my sample space, then the probability of that happening is 1. Rule number 3, in the case of equally likely outcomes, we can calculate probabilities in this regard. The probability of A, it's a fraction. Oops, let me scoot up here. If I want to know the probability of A, I make a fraction here, the number of outcomes that's corresponding to A over the total number of outcomes in my sample space. So this is how we calculate our probability. Rule number 4 is the complement rule. So let's say that this is my sample space and I have all of the elements of inside my sample space, and let's say I want to find the probability of getting A. Okay, well, anything that's not A, I can call a complement. We use a little power here with a C, such that the probability of A plus the probability of a complement is equal to 1. Alternately, you could write it this way. You could say the probability of A is the probability of 1 minus its complement. So that's what we did up here. So when we were doing this 1 minus probability of x minus 0, we were dealing with complements there, so that an event and its complement add to the whole sample space. Okay, rule number 5. This is going to be a big one. This is called the addition rule for mutually exclusive events. AKA disjoint events. Okay, super important vocab word to know. Mutually exclusive or disjoint. They mean the same thing. Okay, so if I have my sample space and let's say that I have two events that have no elements in common. So let's say we're talking about juniors and seniors. So I've got students that are juniors, I have students that are seniors. You can't be both. So J is junior and S is senior. So these are considered mutually exclusive or disjoint events. So what the rule says is that if you want the probability of A or B, if I want to be a junior or a senior, I take the probability of A plus the probability of B. So that's exactly what we did up here. So if I want to be looking at the number of heads and 3 flips of a coin, and I wanted to know x greater than or equal to 1, probability of getting at least one head. That means that I could have one head out of 3 flips, 2 heads out of 3 flips, or 3 heads out of 3 flips. I can't be all. I can't do them all. So this is x equal to 1, or x equals 2, or x equals 3. And each one of these events were disjoint events. I could put them in separate bubbles. So what's important also is that if you are looking at A and B, can I be in both A and B at the same time? And the answer is no. And so that's called the null set, or 0. So these are your first 2 formulas, but you have to be really careful. These 2 formulas are only true for disjoint events. We're going to see other events that are not disjoint, that are joined events, and so these probability rules don't apply in that case. So let's just do a little bit of practice. So here we have some data on some AP scores. Randomly select a student who took the 2010 AP Stats exam and record the student's score. Here's the probability model. So it says, show that this is a legitimate probability model. Okay, so to show it, it means that you're going to add all these probabilities together. 0.233, 0.183, 0.235, 0.224, and 0.125. And if they all add up to 1, then that means that it's legitimate. Does it? Yes. So that's a legitimate probability model. Okay, so then it says, find the probability that the chosen student scored a 3 or better. So the probability that my student, so I'm going to call this x, and here's my p of x. Oh, I didn't mean to close that. So 3 or better means greater than or equal to 3. So this means p of x equal to 3. Now, can you have a 3 and a 4 at the same time? No, so these are disjoint events. Either you got a 2 or a 3 or a 4 or a 5. So that means that I can just add these all together. So we add 0.235, 0.224, 0.125, and we get 0.584. Find the probability that the chosen student didn't get a 1. Okay, so didn't get a 1, so that's a 1 complement. So you can work this in one of 2 ways. It depends on how you like to think. So I can do the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 5, or you could do 1 minus the probability of 1, and in all cases you get 0.767.